So I'm Brian Korgel, Director of the Energy Institute. Thanks for coming this morning. This is the 10th annual UT Energy Week, so very excited, 10th anniversary of Energy Week. We've got a great program. So today is a mixture of research presentations. So I took over as Energy Institute Director about 2.5 years ago, and during that time, we've had 3 seed research programs, one called Energize, which was focused on collaboration between UT Austin and Southwest Research Institute. Another seed research program that kicked things off where we had 17 one-year $60,000 projects, so we'll hear from those folks. And then last year we had our strategic seed program, which was industry funded, and so that funded 9 $100,000 one-year projects. So we'll hear the results from those as well. For this year's strategic research call, we have funding for 12 $100,000 projects, and we got 61 proposals. So good luck to y'all if you submitted a proposal. Really, really exciting ideas in there. All right, so we're going to go ahead and get started. Is the first speaker ready to come on up?
This one?
I think you just start talking.
Oh, okay,
yeah,
cool.
Works.
Yeah. Hi, good morning, everyone. It's our great pleasure to be here, to be the first team, and talking about the work done by our team on the computational investigation of biocatalysts for CO2 reduction. And this is our team. We have 2 presenters today. I'm Yunling. I'm from the Lu Lab and a postdoc. And my collaborator is Mohan. He will talk about the method and the key findings. And he comes from the Oden Institute, from the lab of Dr. Luru. So we all know that the atmospheric CO2 level is ever increasing, which causes severe environmental problems such as global warming and ocean acidification. And to tackle this problem, it's important to develop effective capturing and the conversion of CO2 to useful chemical compounds for daily life. And to do that is actually very difficult. From the perspective of a chemist, it's very hard to activate and convert CO2 because it's a very inert chemical. And nature has evolved organisms to deal with this issue, to evolve organisms which can rely on CO2 to fix carbon dioxide into chemicals for the metabolism. And the key to the function of those organisms are the involvement of metalloproteins. To mimic the function of those metalloproteins for CO2 fixation and conversion, we designed biocatalysts built upon very small and simple proteins such as myoglobin. So myoglobin, its native function is to bind, store oxygen in your muscle, but we engineered the function of this protein to reduce CO2 into CO by simply removing the metallic cofactor in this native protein with a cobalt buffering. And we can achieve up to 1,000 turnovers of CO2 into CO conversion under the photocatalytic conversions. By saying photocatalytic conversion, we mean that we feed chemical photosensitizers as well as reductant with our biocatalyst, and under the irradiation of visible light, we can actually convert carbon dioxide into carbon monoxide very efficiently. However, compared to the native enzyme, it's still very low in terms of the turnover, how many times we can convert CO2. To further improve our catalyst, we involved the methodology of computational calculation to understand deeper about the mechanism of our biocatalyst. So now I will welcome my colleague, Mohan, to talk about the methodology as well as the key findings that we have.
Hello, everyone. My name is Mohan Teja. I'm from the Mechanical Engineering Department. And now I'll be talking about the computational methodology as well as some preliminary results that we have. So in order to deal with the large biomolecular system that we have in the experiments, we adopted a hybrid QMMM method. So in this method, basically the cobalt porphyrin as well as a few surrounding residues are dealt with at the DFT level of accuracy, whereas the rest of the system, which is not really that important in terms of chemical reactions, is dealt with using molecular mechanics force fields. And the way we selected the number of protein residues to consider is by computing the electrostatic potential at the cobalt site for increasing radius of the QM region, and at about 8 angstroms we see a saturation in the electric field at the cobalt site, and that is what we considered for further experiments. And the first step was to benchmark the developed methodology to see if the system well represents the experimental findings. We started with the structural property by computing the average cobalt-nitrogen bond distances, and they seem to match pretty well with experiments. And the next thing we computed was the UV-vis adsorption spectrum for cobalt-2 and cobalt-3 systems, and we observed a similar redshift that was observed in experiments in our computations as well. Next, coming to the results, the first main result that we observed is that in order for this reaction to start, a single reduction of cobalt-2 to cobalt-0, or a double reduction of to cobalt-1, or a double reduction of cobalt-2 to cobalt-0 was necessary, because the CO2 would not bind to cobalt-2, but it would bind to cobalt-1 or cobalt-0 systems. And the next result that we observed is that in order to transfer a proton successfully from nearby sources, which is the histidine residue or a nearby water molecule, a further reduction of cobalt-1 to cobalt-0 was required. And we also identified two possible reaction mechanisms for this. In the first step, hydrogen can directly transfer from a histidine residue. In the second step, hydrogen transfers in a concerted way, where it transfers from the nearby water molecule to the bound CO2, and then the hydroxide ion extracts a proton from the histidine. And right now, we are in the process of computing the binding energies for both methods. Yeah, thank you.
So finally, as a summary, we have identified the most promising oxidation state of the cobalt epoxide, which can bind and reduce CO2. And we also figured out the proton transfer mechanism for the first step of proton transfer onto the carbon dioxide substrate. So for the following studies, we will continue to calculate the full energy landscape associated with the CO2 activation and reduction all the way into CO, and also develop the machine learning framework to identify the possible favorable mutations inside the protein that can further enhance the CO2 reduction efficiency. So that's all for our presentation, and you're welcome to come to our poster for further discussions. Thank you.
All right. All right, speaker 2 is here. Great. So the next talk is combining quantitative leakage risk assessment with financial liability for CO2 geologic storage. Great.
All right. Thank you very much for the introduction. My name is Sahar Bakshian. I'm a research assistant professor from the Gulf Coast Carbon Center. So our project is focused on combining quantitative leakage risk assessment with financial liability for CO2 geologic storage. So before I start, I would like to thank my students and my colleagues who were collaborating with me on this project, and a special thanks to Energy Institute for supporting our project. Okay, so when we store CO2 in geologic formation, one of the main investment risks is the cost risk. If the storage fails, or if CO2 or brine or resident brine leak to the underground sources of drinking water, that we call it USDW, or to the atmosphere. So legacy wells, if they are failed or improperly plugged, they can be the most likely leakage pathway for CO2 and brine. So based on an estimation by Environmental Protection Agency, EPA, in 2018, it was found that we have 3.11 million abandoned oil and gas wells nationwide, and 69% of those wells, equivalent to 2.15 million of those wells, are not even plugged. So those can be, the most likely leakage pathways if they penetrate the storage zone. So even though the environmental liability of leakage from those plug and abandon wells is one of the long-term liability for CO2 storage projects, however, the financial liability has not been addressed by the insurance sector properly. So the objective of our study was to basically quantify the leakage risk through these legacy wells if they penetrate the storage zone. And then finally, using the environmental risk assessment, we plan to constrain a cost model to come up with a financial impact of leakage phenomenon. So as for the leakage risk assessment, we couple reservoir and wellbore modeling to predict leakage rate and mass of CO2 and brine through the legacy wells from the storage zone to different environmental receptors, including USDW and to the atmosphere. And then we consider uncertainty in geologic and flow characteristics, as well as quality of failed wells to quantify the impact of these uncertain parameters on the risk assessment. As for the environmental impact analysis, we consider different environmental receptors, including atmosphere and underground sources of drinking water. However, in this presentation, I'll just only focus on the USDW, which is one of the main concerns for EPA in terms of risks related to CO2 storage. So as for the methodology, we used reactive transport modeling to consider geochemistry and combine it with multi-phase flow modeling to quantify the environmental impact of CO2 and brine leakage on the quality of groundwater resources. As for the metrics that we quantified using those simulations, we track changes in the pH, total dissolved solid, or TDS, major and minor elements, and mobilization of trace element in USDW. And finally, to quantify the radius of impact, we compared the variation in the quality of groundwater resources with EPA primary and secondary drinking water regulations. And then finally, using risk assessment, we were able to quantify risk maps that shows spatial and temporal distribution of leakage risk around the injection well. So as for the financial risk assessment, we consider different cost models in our financial model, including considering preventive strategies, including considering diagnostic monitoring wells, as well as considering different remedial response actions to any leakage events. As for the remedial response action, we consider different scenarios, including groundwater extraction and treatment, extraction of impacted water coupled with injection of clean water into USDW. And also we consider scenarios, cost scenarios for any injection interruption due to any leakage event to USDW. As for the conclusion, so regarding the environmental impact, we found out that CO2 leakage dictates pH variation, pH drop in USDW, and consequently it causes release of trace element in groundwater resources. And brine leakage may not impact groundwater quality as much as the acidity of CO2 dissolution into USDW. And as for the financial impacts, we found that it is mostly dictated by the geology of the storage zone, by the nature of the leakage event, characteristic of the groundwater quality, the type of diagnostic monitoring system that we are going to consider, as well as any remedial action or response plans that we consider for a remediation of leakage. And finally, the majority of those costs can be driven by CO2 leakage than brine leakage. Thank you so much for your attention. I'd be happy to take your question in the poster session.
All right. So Krista, is there a way to do the presentation mode? Okay. Great. All right. Speaker number 3. Thanks.
All right, so, thank you all for coming out. This is a project that was, has been kind of a really cool pet project of mine and our teams for a while here. And we're really grateful for the support of the Energy Seed grant for getting this project going. I'm going to talk a little bit about, what might happen when we take into consideration the sort of actual nature of the geochemistry of CO2 injection, as well as with our kind of man-made constructions associated with that. So just to kind of go over it more broadly, right, we are taking CO2 and putting it in the ground so it doesn't go into the atmosphere. This requires a lot of CO2. Why we do it is because we can put a lot of CO2 in the ground, and that's its main benefit. But when you put a lot of CO2 with water at high pressure, you get carbonic acid, and that'll come into play in a second. But as Sahar was saying, we have a lot of wells, especially in Texas, that may be poorly maintained. But if you look on the right here, you can see that for the most part, if CO2 was to leak through this, it would have to go through cement of some kind. Yes, maybe that's nice plug there in the middle might not be there, but that's a pretty rare occurrence, I would say, at least on every single well that I've worked on. And so what happens when carbonated water interacts with that? Well, it's actually kind of the perfect storm of chemistry here. We have primarily, Portlandite. It's not a real mineral exactly, but it's just cement really, or the primary component of cement is calcium hydroxide. So it's like a perfect component for reactions with carbonated water. Basically, simple chemistry here. The pH is very low when you have acidic CO2 saturated water. It dissolves some of the cement, which is primarily Portlandite. I'll maybe mention some of the other components as well. Also these calcium silicate hydrates, essentially increasing the pH and buffering the solution. And so the solution drives the reaction towards the creation of free calcium ions and free carbonate ions, and it becomes so carbonate rich and high pH that it then precipitates out. So basically, when it's first introduced, it dissolves the fracture a little bit, but then it precipitates out and can end up clogging it. So maybe this, very critical leakage pathway may have some sorts of chemical components that may slow down the actual leakage process when investigated a little bit more. This is kind of what it looks like. And then so how we approached investigating this further was by the creation of this experimental setup where we make these thin chips of cement straight from, basically straight from the field, where we might construct these wells, Class H cement, same kind. And so we cure it in the absence of oxygen and CO2 and a special series of chambers, and encase it before it sees, we cut it and then we encase it in this silicone PDMS material, fracture it while it's in that material, and then flow through it. And what we can see is kind of the most recent developments in this study. We studied it more from fun kind of basic nature, but the recent developments are comparing some of the chemicals used in the oil and gas industry and how those might influence this process. And so we looked at it, this flow test with and without the presence of a surfactant. And we saw some interesting things, and I always find it pretty interesting to see some of this stuff up close. This is quite small, about 12 micrometers wide here. But we can see this is created by this process, these rhombohedron shapes. This is just calcite, pretty standard, but what we can see here is that without the presence of the surfactant, we had some preliminary tests where it clogged, but when we made this comparison in a very controlled setting, we found that without the surfactant, these rhombohedrons form quite nicely, but then grow so big that they potentially detach and flow downstream. And so in our setup, we can't really capture the fact that we might be clogging it up with a bunch of different little cube precipitates. So we kind of get a buildup and then a drop off and a buildup and a drop off because we expect it that it keeps breaking off. But with the surfactant, we kind of have an even buildup. And so the surfactant kind of, our hypothesis is that it creates a protective barrier once it's formed initially, and then so it creates a bunch of different ones, and then it eventually grows so you know, that coating kind of grows so large that the aperture closes up, and we do find that that we get some clogging here. And then so the idea being that these like chemicals used in the oil and gas industry may be tuned to you know, our benefit to make this effect better, but also that their presence ends up clogging these fractures even better than the sort of pure water case or pure geo-water case. And I think we're really happy to see that, and I think there's still some great work. So thank you for your time, and again, I suppose I'll be at the poster. Thank you.
Great. All right, speaker number 4. So since we got started a little bit late, as the speakers coming up, a couple things. So we've got the research presentations grouped by topic. So as you can tell, this morning's carbon capture, utilization, and storage. And then the speakers will all have posters during lunch for about an hour. So we've got CCUS and then clean hydrogen this morning, and then posters where you can dive in. I have tons of questions, so I'm looking forward to the poster session. Thanks, go ahead.
Good morning, everyone. My name is Awan, and I'm a PhD student in mechanical engineering, and Dr. Vaibhav Bahadur is my advisor. Today, I'll be talking about carbon dioxide hydrates-based carbon sequestration on the seabed. So essentially, the idea is to create a new technology for carbon sequestration using hydrates. Now, what are hydrates? Hydrates are these ice-like materials where water molecules are bonded together with hydrogen bonds, and they're entrapping a gas molecule. Today, we're talking about CO2 hydrates, so they're essentially entrapping CO2 in our case. The CO2 can be a liquid or a gas phase. They are stable at moderate temperatures, lower temperatures and moderate pressures, like 30 atmospheres and 1 to 4. These conditions are met in the seabed, which is why we're proposing hydrates-based sequestration on the seabed. One thing to note is that they're denser than water, so essentially they would sink towards the bottom of the ocean and stay there stable. One issue with this technology is that, or one challenge for this technology is that if hydrates are left open in contact with seawater, they will eventually dissociate, so you need some form of artificial sealing around it. So in order to make this thing happen, we are proposing a 4-step process. Essentially, you would start with making hydrate slurries, and then transport these slurries to compact them into plugs where the density is increased and excess water is removed. The hydrate plugs will be needed to be sealed with an artificial sealing, and then they can be disposed of on the seabed and monitored. For the sealing, we will need a lot of attributes. For example, they need to be CO2 impermeable, needs to be bio-friendly, it needs to be flexible, tear-resistant, burr-resistant, durability, to name some of them. Now, some of the work that we have done in our group for this includes numerical modeling, techno-economic modeling, and experimentation. We have learned that if we were to run a reactor in a continuous flow system, then we can increase the total rate at which CO2 is consumed by 6 times than the standard that is done in the literature. In the numerical modeling end, we're looking at hydrate slurry transport, and if we can easily transport hydrate slurries, because it can lead to issues like choking. Now, as far as the techno-economic model is concerned, we are looking at a 30-year project duration, and we are seeing that most of our costs come from refrigeration. So if we were to implement this idea on the seabed, we would be able to reduce some of those costs. Second highest cost contributor is compression. And we are looking at an average cost at $36 per ton for 1 reactor. If we are to increase this number of reactors and increase the scale of the sequestration from 1 megatons per year to, let's say, 10, then we would look at the cost at about $25 per ton. The energy consumption for the same is about 260 kilowatt hours per ton, and the electricity cost Our electricity contribution to the total cost is about 50% at $18.5 per ton. That's about it. I will be outside at the poster for any questions.
All right. So next talk, impacts of geochemistry on carbon dioxide adsorption in organic-rich mudrocks.
Good morning, everybody. This is Ibrahim Goma from the Hildebrand Department of Petroleum Engineering. Today I'm going to present my work to you about the impacts of geochemistry on carbon dioxide adsorption during CCUS operation in organic-rich mudrocks. Thanks for the Energy Institute and Sea Grant for sponsoring part of this work. This work is carried out under supervision of my advisor, Professor Zoe Haidari, and Dr. Nicholas Espinosa. As you may all know, we need to store huge amounts of CO2 underground. One of these options is store it in organic-rich mudrock reservoirs. Why we may choose organic-rich mudrock to store CO2? This reservoir has a special nature. They have a wide range of different pores, starting from macro pores, micro pores, and nanopores, which provide huge surface area for adsorption. In fact, CO2 sequestration mechanisms such as reservoirs can be divided into adsorption, residual solubility, and mineral trapping, while adsorption carry out the main weight of the sequestration mechanisms such as reservoirs. However, one of the many challenges of injecting any gas or any fluid in such reservoir is their heterogeneity. With kerogen or the organic matter and the clays being the more contributors to the adsorption operation of the CO2. So we need to study the parameters related to these two kinds of rock components that can affect the adsorption or the storage of CO2 in such reservoirs. How are we going to tackle that? We have two approaches. The first one is using molecular dynamic simulation, in which we model different types of kerogen that represent a major component of the organic matter, organic-rich mudrock, at different types and different thermal maturity. We also modeled different clay models with different cation exchange capacity, surface charge, and atomic structure. The other part of this research is using lab experiment to evaluate the adsorption of different gases and these pure components and the mixture of these components under high pressure, in which we can flow pure gases and also a mixture of these gases to evaluate the adsorption capacity of such rock components. And today I'm going to show you some of the simulation results that we had. As you can see from all the plots on the top row, the y-axis represents the total amount of gas that got adsorbed, and the x-axis represents the gas pressure injected. The first plot from the left shows that the impact of kerogen types. We have three types, 1A, 2A, and 3A. As you may see that changing the kerogen type from type 1A to type 3A got increased amount of gas or the CO2 that can sequestered or adsorbed by this kind of formation by 4 times. Moving to the impact of thermal maturity, the more thermal maturity or the higher the thermal maturity, the higher the CO2 that can be adsorbed by such models, like going from type 2A all the way to type 2D, which is like post-mature kerogen. We approximately doubled the amount of CO2 adsorbed in such models. And the third plot shows the impact of temperature on the adsorption process. Since adsorption is an exothermic process, as we increase the temperature, we decrease the amount of gas that can be adsorbed or stored. So it's very important to look into the reservoir temperature when you apply CO2 sequestration in such reservoirs. And finally, for clays, here we had 3 types of clays. One attached to positive cations, such as potassium. One has almost neutral surface, such as kaolinite, and one has negatively surface charge, which is light. As you can see, the charge of the clay surface played a very important role in CO2 sequestration. And if we are targeting enhanced gas recovery in such reservoirs, it's very important to look at the selectivity of CO2 over methane in such reservoirs. As you can see, the plot in the middle down row, so the selectivity of CO2 over methane for such kind of reservoir at different pressures. So as you can see, like higher selectivity, higher than 1 is favorable, more favorable for enhanced gas recovery options. And as you may see, like corrosion type, thermal maturity, clay surface charge all also affected the selectivity of CO2 over methane in such reservoirs. So in conclusion, compositional evaluation is very important when you carry out CO2 sequestration in such reservoirs, and numerical models besides experimental work can enhance our judgment for choosing the optimum condition for CO2 storage in organic leach mudrock. I will be happy to take your question during the poster session. Thank you.
All right, thanks very much for that. The next talk is laboratory experiments and modeling to accurately evaluate critical CO2 saturation for geologic carbon storage.
Hello, everybody. I'm Jose Yubilis from the Department of Petroleum and Geosystems Engineering. First, I'd like to acknowledge my advisors and all my team at the Gulf Coast Carbon Center, and a huge thanks to the NRGC for being part of the funding of my project. So today I'm going to talk about my master's project, laboratory experiments modeling to accurately evaluate critical CO2 saturation for geologic carbon storage. So when we inject CO2 underground, initially the fluid moves as a compact mass close to the injection well, but farther away from the injection well, it moves like fingers and it accumulates below capillary barriers. The fluid will percolate through the capillary barriers in places where the buoyancy pressure is high enough to overcome the threshold capillary pressure. In this zone is where small-scale heterogeneities are very, very important, as they can retain and slow the CO2 plume. So when not properly upscale, these small-scale heterogeneities can lead to inaccurate field-scale simulations, which at the end is what is most important. For instance, here, this is a simulation domain, and we can see that when the saturation per grid block changed from 3% to 48%, the CO2 trapping capacity of the whole domain is almost more than doubled, from 10 to 21%. So we want to be able to quantify the effect of these small-scale heterogeneities on our simulations. In our lab, we are able to design any type and any degree of heterogeneity. For instance, here I'm showing 4 different types of ripple bed forms. We conduct these experiments at atmospheric conditions, and the fluid is injected through the middle inlet. Unfortunately, I cannot show animations because this is a PDF, but this is the end result of the experiment. So here what we see is the trap saturation within one type of heterogeneity. As we can see, in multiple types of heterogeneity, this trap saturation varies, which means that all simulation will also vary and will have multiple effects. So now we want to be able to incorporate these results onto our field scale simulations. How can we do that? How can we inform our field scale simulation using those experiments? So what we do is we include the trapped CO2 saturation in the inputs of any conventional multi-phase flow simulator, which is relative permeability and capillary pressure curves. So we can include this trapped saturation as the critical gas saturation, which is the first non-zero value, either just in the relative permeability curve, or if you use a modified capillary pressure curve, you can also include this critical saturation on the capillary pressure curves. Now, basically our result shows that when we increase critical saturation, that means when we change type of heterogeneities, the plume shape and the lateral extent of the plume decreases, which is a very important takeaway when we do field scale simulations. And it's also important for EPA regulations. In the image on the right, I'm showing these results when we increase critical CO2 saturation from 0.1 to 0.3. basically the plume reduces. This is all I have to tell you for now. I'll be in the poster session, so if you have any questions, just come and see me. Thank you.
All right. Next talk is long-term surveillance of plugged and abandoned wells for immediate detection of CO2 leakage in geologic carbon storage sites.
Thank you so much. It's me again. So our project is focused on long-term surveillance of plugged and abandoned wells for immediate detection of CO2 leakage in geologic carbon storage sites. So I would like to thank my colleagues and my collaborators from the different consortia at the BEG, at the Bureau of Economic Geology, for collaborating with me on this project. My colleagues from Advanced Energy Consortium and Texas Soil Observation Network who are contributing to this project. So the objective of this study was to design a cost-effective monitoring system for long-term surveillance of plugged and abandoned wells. So we designed a shallow control release experiment, so it's a field-scale project. We designed a control release experiment in which we have CO2 and water leakage from a plugged and abandoned well, from a proxy well, and we deployed a monitoring package above in the VADO zone, above the proxy well stop, to monitor soil signatures, including soil moisture, soil temperature, soil electrical conductivity, as well as temperature variations inside the well casing during any leakage events. So we also have a weather station to kind of measure the environmental variability in any atmospheric conditions, including precipitation, air temperature, wind speed, and wind direction, and so on. So because we are running the experiments in VADO zone, it's a noisy environment, and sensor data can be impacted by any atmospheric variability, including precipitation, changes in the humidity in the air, or changes in the air temperature. So the idea is to kind of capture any environmental variability in the system, as well as any anomalies that we see during the leakage events, and finally use machine learning to separate these two different signals, these different source of anomalies in the sensor data. So here are the steps that we went through to set up the experimental area, which is conducting, the experiments are conducting at UT's Brackenridge Field Laboratory. So initially we excavated a trench and placed a metal casing in the middle of the trench, as well as PVC pipes for CO2 and water injection into the leakage zone. And then we placed different sensors to measure soil properties, as well as some microsensors that our colleagues have developed, manufactured to measure soil temperature. At different depths, we place the sensors at different depths and different distances from the leakage point. And then we backfill the trench with a mixture of natural soil and engineered sand. So to kind of measure and check the response of the system to any environmental variability, we collected some background data in a few days, and you can see in this figure the changes in the soil temperature, soil air temperature, as well as temperature variation inside the casing over the time that we gathered the data, the background data. And what we observed was that the system was very responsive to any diurnal variation in any environmental variability. So as well as the soil moisture that we collected, it was very responsive to any precipitation events or changes in the air humidity. We ran some experiments for water leakage and CO2 leakage. As for the water leakage, we heated the water up to 34 degrees C to kind of simulate the same scenarios that we have related to brine leakage coming up from the subsurface reservoirs, which are basically at high temperatures. So we heated the water and inject water for a few hours, and you can see the response of soil moisture and soil temperature variations during the leakage event that we had. So we observed that soil moisture and soil temperature, as well as electrical conductivity, in the soil at deeper locations and in the proximity to the casing, to the well casing, responded very well to the hot water release. However, the response of casing was more prominent than the response of the soil temperature because of the higher conductivity of metal compared with soil. And then as for the CO2 leakage, we ran several experiments for CO2 leakage, and you can see one of the experimental results here that shows the changes in the soil electrical conductivity when we had CO2 leakage. And what we observed was that the leaked CO2 elevated the soil electrical conductivity due to the dissolution of CO2 in water content. And because of the release of carbonic acid, when we have CO2 dissolution in water, we observed an increase in electrical conductivity in soil during the experiments. So based on the experimental results, we are confident that this experimental setup is successfully responsive to any leakage events. And our next step to implement machine learning to separate anomalies that we see because of the leakage event, and separate it from any anomalies that we see due to the environmental variabilities. Thank you so much for your attention. I'll be happy to take your questions during the poster session.
All right. So next talk, enabling zero carbon emissions by electrochemical CO2 reduction technology.
Hello, everyone. It's an honor to present our work about enabling zero carbon emission by electrochemical CO2 reduction technology on behalf of our team, including myself, Ruoyu, Kevin, and our professors. We greatly appreciate UT Energy Institute and partner companies for supporting our research. First, I will briefly go over the ECO2 reduction technology background. The excessive emission of carbon dioxide has a serious impact on the environment and human existence. People try to solve these challenges by CO2 capture, utilization, and storage. Among these methods, the electrochemical reduction of CO2 is very promising due to these advantages. The reaction can be operated at ambient temperature and pressure. The products can be controlled by different parameters and others. So we aim to convert CO2 to high value-added products in a low-cost, highly efficient, and sustainable way, which are intended for further industrial application. So we have designed a kind of fluorine-doped carbon blend-based nickel single atoms to convert CO2 to CO. This catalyst exhibits nearly maximized atom utilization efficiency due to every single nickel atom works as a reaction center. And the carbon black-based material and the facial preparation process also contribute to the low cost and large scale preparation of our materials. And to further enhance the permanency of our materials, we dope it with fluorine to further modulate the electron configuration of the central nickel site. We then characterize composition and structure of our materials by different characterization techniques. Half STM is a kind of scanning transmission electron microscopy technique that can provide atomic resolution image of the materials. We have found that the nickel atoms are dispersed uniformly and individually among the carbon matrix. And no related nickel nanoparticles have been observed in our materials at this site according to the XRD test. In order to further investigate the electronic states of the elements in our sample, we conduct X-ray photoelectron spectroscopy. We can find that the doping fluorine influences electron distribution of the nickel site. and different states of the elements in our samples have been observed. We can find that such as semi-ionic fluorine at this site, ionic fluorine at this site, and different states of nitrogen in our samples. We also try to investigate the influences of the different states of the elements on the performances by DFT calculations. After then, we try to investigate the properties of our samples. Current density is one of the parameters can characterize catalytic activity. The higher the current density, the more CO2 can be reduced into products at a specific voltage stimulation. We can find that the performances can also be adjusted by varying contents of the fluorine doping. And the catalytic activity of our sample is also very significant compared to the reported materials. And ferritic efficiency is also one of the parameters to characterize the selectivity of the catalyst. It's about how well we can turn electrical charge into desired material. The higher the ferritic efficiency, the less byproducts can be generated in the reaction. We can find that the CO ferritic efficiency maintained about 90% in a wide potential window. And the high turnover frequency also indicates excellent activity of our catalyst. We also try to conduct the DFT correlations to further investigate how fluorine atoms promote the performances of our catalyst. That's all our work. Thank you.
All right, thanks. The next talk is Study CO2 Foams in an Effort to Improve Long-Term Carbon Storage in Depleted Oil and Gas Reservoirs. And I guess the speakers try to focus on using the microphone while you're up there.
Well, good morning, everybody. My name is Masha Pradanovic, and I'm one of the investigators on this project. So you've heard the word foam. Your favorite foam in the morning might be the one on top of your cappuccino. In the evening, maybe on top of your beer. Well, while that's enjoyment of your drinks, in subsurface applications, we use foams because they actually viscosify. So you have a lot of bubbles. That's texture of the foam. And we also look at quantify the content, what is the actual gas content. And these bubbles are in a liquid carrier. So that's basically how we define foams. And one major property of the foams, well, I got off on a tangent to introduce foams, but before I move on, I will actually introduce this collaboration. So it's collaboration between UT, David DiCarlo, Yevgeny Samarkin is here in the audience. He's going to present the poster. We have a student that just graduated, so we have a turnover, Anuradha Radhakrishnan, so she's now Dr. Radhakrishnan. And that is the UT team, and Southwest Research Institute at San Antonio is doing the collaborating part on a larger scale. Sarah Wheeler, Luke Morris, Angel Wildman, and also recently Tajik Rauf are part of the team. So to continue my talk on the foam, why we're interested about them in the subsurface is the viscosity. So gas has very low viscosity. If you're trying to inject gas, and we'd like to inject CO2 for storage, it is going to be very unstable, and the plume is probably going to rise up, as you've seen in some of the presentations just before. So if you inject foam, these bubbles provide a lot of resistance, and that's the viscosity, that's measured by viscosity, and you will have much more stable displacement front, and therefore hopefully much more stable injection. However, the main problem with the foams is actually maintaining these bubbles, which is also referred to as a stability of the foam, especially in the presence of high pressures and high temperatures, such as those in the reservoir. So the main objective of this proposal is to basically see what does CO2 foam do in the presence of various types of heterogeneities in subsurface. By heterogeneity, I mean we always have fractures, interfaces between different types of formations, and so forth. So Basically, on the UT side, we're doing what we call lab scale, your regular core scale investigation in fractured sandstones. So you can see an example of the sandstone here, as well as our oven, where we actually keep everything on a desired at the desired temperature. Whereas at Southwest Research Institute, we have much larger, what we refer to as a pilot scale. That size of an experiment is very unusual in a university setting. And there, instead of fracturing a core that is this long is also a problem as well. So we look at the heterogeneities between two types of sand. And basically you have formations of different types of permeability. You can see that interface right here between the two types of sand. And again, it's much of a larger setup. I will just present a teaser, and for more information, you can visit the poster. So basically, these are sandstone, Berea sandstone results, and you can see initially we generate foam, which is the yellow curve, the top curve here on the, here it is. So you can see these viscosities. So mind you, viscosity of water, for instance, is 1 centipoise. So we go up to 50 times more than that. That's this viscosification. However, as you inject it into a fracture, which is heterogeneity, it's going to drop some, and we quantify how much, versus the quality, which is, again, a percentage of gas within. However, right after you exit the system, you're going to basically have a foam collapse, and that's something that we're trying to prevent. So these are our core scale experiments. On the large scale, we already looked at some problems. So basically, we were not able to maintain a stable foam, which probably means that there is a leakage path of some sort which caused the foam collapse. So this is something that we are right now working on changing. We also did not maintain a stable temperature in that experiment, or rather, Spheri did not maintain a stable temperature, so they're right now building the setup that is actually much more temperature controlled. So I hope we have much more to present next time on this slide. Thank you.
Thank you. So the last CCUS talk is CO2 pipeline flow behaviors as part of a larger effort to facilitate large-scale carbon capture, utilization, and storage.
Hello, good morning, everyone. I'm Fuzhou Bai. It's my great pleasure to stand up on behalf of our teams to present our research project on the study CO2 pipeline flow behaviors as part of the larger effort to facilitate large-scale carbon capture, utilization, and storage. So let me first give an introduction about the CO2 transportation. So it's known that the CO2 is the primary one of the greenhouse gas that cause the global warming issues. And the CO2 emissions has been increasing yearly in the world. By 2017, there is more than 66 billion metric tons per year CO2 emissions. So to achieve the net zero CO2 emission by 2050, the CCUS has been regarded as the most potential and efficient technology to reduce the global emissions of CO2. In particular, the CO2 transportation serves as an interface between the carbon sources and the storage site, which is important for the CCUS. Currently, there is more than 27.9 thousand miles of the pipeline are required for the CO2 transportation. However, there is very limited experience on the transporting anthropogenic CO2 for CCUS purpose. The main challenges are including following aspects. First is the two-phase CO2 flow occurring in the pipeline, and then the impurity effect on the CO2 physical properties, and the last is the dynamic flow conditions for long-distance CO2 transportation. So to achieve an efficient CO2 pipeline transportation for future CCUS, our project includes following three tasks. The task one is the study of the flow behaviors of the two-phase CO2, including the experimental testing and the model development for the two-phase CO2 pipe flow. And then the task two comes to the impurities effect on the thermophysical hydraulic properties of the anthropogenic CO2. In this task, we will identify the suitable thermophysical models for CO2 mixtures and then grade the effect of each impurities. Then the last task is to develop a dynamic model for the long-distance supercritical CO2 transport in pipelines to monitor the pressure, temperature, density variations along the pipeline in a slow transient flow conditions. So here shows our current research result for the two-phase flow behaviors. A two-phase CO2 test facility are conducted in Southwest Research Institute, and during the two-phase flow transport in horizontal pipeline, only the following flow patterns are observed, including the stratified annular and the stratified flow. And then in addition, a robust drip flux model for two-phase CO2 is developed. The model is validated with the experimental data, and then by comparing the performance of our model with the 3 other existing CO2 transport models, our model has the best performance in pressure drop prediction within the 5% error. And then in the context of the effect impurities, we use the EOSCG, which is the most accurate method for the binary CO2 mixtures to calculate the properties of the binary CO2 mixtures deviation from the pure CO2, including the vapor-liquid equilibrium, density, viscosity, and the pressure drop. And then each impurities effect was ranked in following parameters. We found that the hydrogen has the largest effect and the hydrosulfide has a mild effect. Last of all, the long-distance supercritical CO2 transport, a dynamic simulation model for supercritical CO2 is developed. So due to the lack of the experimental data cannot be found in any literatures, the model is validated with the commercial software OGA. So from the result, we can see that our model has the reasonable accuracy, and then compared to the OGA, our model can achieve faster, stable simulation conditions than OGA. So that's all for our research. Due to the time limitations, if you have any further discussion, please come to the poster section. Thank you.
All right. So that's fascinating. I mean, it's really interesting to see all of the work going on at UT related to CCUS, all the way from CO2 reduction and conversion to pipelines to storage, leakage detection. So really fascinating. Great presentations.